Hello and welcome to today's session. This session focuses on learning outcome 2LO2, understand benzene rings. In this video, we will explore what makes benzene rings unique in chemistry. You will examine the structure and behavior of benzene as a key aromatic compound and understand why its exceptional stability and reaction patterns differ from those of typical unsaturated compounds. A benzene ring is a 6-carbon structure found in aromatic compounds. Its molecular formula is carbon 6, hydrogen 6. Although it appears unsaturated, benzene behaves differently from alkenes. This behavior is due to its unique electron arrangement. Understanding this structure is key to grasping its chemical properties. Each carbon atom in benzene bonds with 2 carbons and 1 hydrogen. 3 sigma bonds form, leaving 1 electron per carbon unbonded. These electrons are delocalized, spreading evenly around the ring. This electron cloud forms above and below the molecule's plane. Such delocalization is often depicted as a hexagon with a circle inside. The delocalized electron system is benzene's key feature. This system enhances molecular stability and equalizes bond lengths. Unlike typical alkenes, benzene resists addition reactions. Breaking this electron system requires significant energy. Thus, benzene prefers reactions that maintain its ring structure. Benzene displays resonance stabilization, unlike typical alkenes. Addition reactions would disrupt its delocalized system. This disruption demands high energy, making these reactions unfavorable. Benzene instead undergoes reactions, preserving its structure. This unique behavior highlights its distinct chemical nature. Benzene primarily undergoes electrophilic substitution reactions. Here, a hydrogen atom is replaced, keeping the ring intact. The delocalized system is restored post-reaction. Examples include halogenation, nitration, and alkylation. This substitution behavior sets benzene apart from alkenes. Cyclohexene has a localized carbon equals carbon bond. It undergoes addition reactions, decolorizing bromine water. Benzene's delocalized electrons prevent such decolorization without a catalyst. It favors substitution over addition. This comparison often appears in examinations. Benzene is an aromatic hydrocarbon with a hexagonal carbon ring. Each carbon bonds to 2 others and 1 hydrogen. 3 sigma bonds per carbon leave 1 electron delocalized. These electrons form a continuous pi electron cloud. This arrangement leads to uniform bond lengths. Electrophilic substitution is its main reaction type. Benzene's carbon-carbon bonds are of equal length. This contradicts models with alternating single and double bonds. Experimental data supports this uniformity. Benzene's stability is due to its delocalized electron cloud. This stability influences its chemical behavior. Benzene does not decolorize bromine water without a catalyst. This behavior contrasts with typical unsaturated compounds. It supports benzene's unique structure and stability. The delocalized electrons prevent typical addition reactions. This characteristic is crucial for understanding benzene. Aromatic compounds contain benzene rings. Benzene acts as a parent compound for many substances. Substituents on the ring create substituted benzenes. This versatility is key in organic chemistry. Benzene's representation often includes a hexagon with a circle. Delocalized electrons in benzene create a stable electron cloud. This cloud enhances the molecule's stability. It prevents typical reactions seen in alkenes. This electron arrangement is crucial for benzene's properties. Understanding this is vital for chemistry studies. Resonance stabilization is key to benzene stability. It results from the delocalized electron system. This stabilization prevents typical reactions requiring bond breaking. Benzene's chemical behavior is shaped by this stability. This concept is central to understanding benzene. Substitution reactions preserve benzene's ring structure. Electrophilic substitution is the primary reaction type. This reaction replaces a hydrogen with another atom or group. The delocalized system is restored post-reaction. This distinguishes benzene from typical unsaturated compounds. Understanding benzene involves key terms like aromatic and delocalized electrons. Resonance stabilization and electrophilic substitution are crucial concepts. Sigma and pi bonds define benzene's structure. These terms form the foundation of benzene chemistry. Mastering them aids in grasping benzene's unique properties. In conclusion, understanding the structure and reactions of benzene is fundamental to organic chemistry. Its unique aromatic stability explains both its relative resistance to addition reactions and its preference for electrophilic substitution. Developing a clear grasp of these concepts not only deepens theoretical understanding, but also supports the study of more complex aromatic compounds and their applications in chemical synthesis and industry. For any queries, send us a WhatsApp message at 0748-4361-688, and a team member will be happy to help. Thank you, and we look forward to the next session.